Pleasure to introduce Shrawan from the University of California at North Carolina. Good morning, North Carolina, Chapel Hill. I've known Shrawan for almost 50 years to the day. And so it's a great pleasure. And he will talk about counterexample to a strong Matroid Minor Conjecture.
Thank you very much, Vayanti. And thanks to Milan and Emily for inviting me to give this talk and to be here first time in Sofia. And my very special thanks to Milan for our help to prepare me to come here and yeah. Okay, so what I'm going to talk about is, so there is this strong Matroid conjecture. It will take some time to explain exactly what this conjecture is. So there is a strong form of the conjecture and there is a slightly weaker form of the conjecture. And what I do is that the strong form of the conjecture is false, but maybe the weaker form of the conjecture may still be true. And as it turns out, the weaker form of the conjecture is, for application, more useful. And then I will tell you what is the connection in combinatorial space to some really important problems in combinatorial space. So before I can come to illustrate the conjecture, I have to explain some notation. In fact, a fair amount of notation. So let's get started there. So okay, there is strategy here. Which one is better? First, I will start on the lower board. Start with the lower board. So Amina explained something. He has some algorithm.
But
Amina has an algorithm.
But yeah, if you can use the top part and then push it up. And then you can use the bottom part as well. But you can.
No, wait. So I use the top part.
Yeah.
And not use the bottom part.
Yeah.
I move it up and then use this, and then use the bottom part. And then use the bottom. Come back to the bottom. Is that part? Okay, very good.
But you bring the front one all the way down.
So
Let me try to explain this.
yes. Okay.
It's put easy.
Okay, all the way down. Okay.
Then you write on this part.
Okay.
Then you raise it up and write on this part.
Oh, so to write half and then
Yeah, so write half first.
Yeah.
And then you raise it up and you can write another half.
I see. But
You have to be the right height for that to work.
I can't write it. No, yeah. Bring it down.
Bring it down.
Yeah, okay.
And write here.
Very good.
And then raise it up and write to the bottom.
Okay. Very good. Okay. So first of all, let K be any tree. I'm not assuming it to be algebraically closed. It can be finite field. Not it can be finite. Actually, it's important that it can be finite field. And let us take two positive integers. N and P. And let's define this space, and just for consistency of notation, I'll just what? V and P. So it's a space with basis x minus n plus 1, up to x minus 1, and then x1, x3. So this is the basis. So it's the K basis. So I take this vector space and let's take Hilbert space. So it's the Hilbert space with dual basis. I will just denote it by x minus n star and so on, x minus 1 star and then x1 star. and x. So just notice that I don't have x0 here. Okay, now let's take Grassmannian of p-planes in V and V star. So this is Grassmannian of p-planes in this vector space. And then we have the blue characteristic. And that involves Grassmannian P, V and V star to exterior P and V and V star as much projected space. And what it does that it takes any vector space W and just maps to P of exterior power. Okay. So this is a projective impedance. So so this makes this object into a projective writing, a smooth projective writing. And now I'm going to take cone. So take the cone. Take its cone, and I'm going to denote this cone by V and V. And cone just means, what does cone really mean? That I take this P, exterior P, and I take this. And now I'm going to take exterior V and start and remove the G. So this is the standard projection map from this function vector space to projective space. And we have an embedding here. We have an embedding here, and we just pull back this. So now this, when we pull it back, we miss 0. So we just add the 0. So this will become a honest, affine subvariety of this vector space. So what I did, that I take this one, I just put this one via this projection, and then I 0, and so this becomes a affine subvariety, honest affine subvariety, and it's a cone. Which is a cone. Oh. Now there are two maps which I'm going to consider. So we have exterior V and plus 1 P star to exterior P, V, and P star. And that is just the restriction map, and I want to write this N plus 1. And this is just the restriction map. So this is the dual of that V and P sitting inside V and plus 1 P. Canonically. So just use the x minus n. So this embeds that. So the dual is rejected, and then this is rejected. So that's what this page. And then there is this and then there is this contraction map. So contraction map, and I'm going to denote the contraction map to be consistent. Yes. So theta and p plus 1. And that takes exterior p plus p plus 1 to v and p plus 1 to exterior v and p star. And this is right. So this takes any form omega 2I xp plus 1. So I'm just contracting omega. So to be specific, what is Ix omega plus 1? So this becomes a degree P form. So if I take, let's say, y1, yp, then this is nothing but omega y1, yp, and then you attach xp plus 1. That's what it is. So I'm making a choice here. You could have attached xp plus 1 in here. So that will only change the sign now. So we have these two maps. So one is the contraction. And another is coming from the map. Now we can combine these. Now these maps. Okay, so now let's go back here. So this Grassmannian, the affine Grassmannian, actually, that's not the right word. Affine Grassmannian is also thought of as Grassmannian in the affine black variety. So, yeah, so I will still call it Grassmannian. So this gives rise to two maps. Grassmannian, that's
Sorry, this is cone over the Grassmannian?
yes,
Okay.
that's one, exactly. So it is a honest cone over the Grassmannian. Okay. So it gives rise to two maps. And I just want to be a bit consistent with my notation. And the other way map which plus 1 p the n plus 1. This is okay. So it's a fairly simple observation that this C and theta induce these maps just by distinction. So this Grassmannian tilde is embedded inside that, and we have defined these maps. So these maps restrict to these two maps. And I am not writing the subscript parent.
I'm sorry, Shrawan, in the contraction, what is xp plus 1? Your basis elements were going to xp, but p plus 1.
So, okay, so omega I did it here. Omega is informed here,
Okay.
right? And now we want to define what is I xp plus 1 omega. So that's a P form now.
Yes.
So now P form means if I evaluate it on V and V star.
Yeah.
So sorry, on V and P. So I take y1, yp, any p elements.
Understand.
Okay, so the yi's are in V and P.
But what is xp plus 1?
Omega started out with V and P plus 1.
See, okay. So omega is a V plus 1 form.
Yeah.
And xp plus 1 is part of the basis.
But you only go to xp in the base.
No, that's it's a dummy variable.
Ah.
For any V, including plus 1.
That's why this intensity is very important.
This is in the p plus first.
Yes,
Very good.
exactly.
Okay. The last basis element of the.
Exactly.
Okay.
Yeah, exactly. The last basic element.
The last
And-
basis element.
And we are both dummies.
Exactly. And I am putting it here. I mean, you could have put it here or anywhere.
Yeah. Last basis element of the.
Exactly. Just to be sure, I put it there. Right? Makes sense?
Good.
Okay, so we have these two maps. Now let's define a partial order on the So, so I'm going to define a partial order. NP is bigger or equal to N prime P prime. If and only N is bigger or equal to N prime and P is bigger or equal. Okay. So, right. Okay, so now I'm going to define a scheme. So, so I'm going to define a affine schemes actually. So this is tilde Grassmannian, and I'm going to let me write it, and I will explain everything in a minute. So let me write, and then I will explain. Okay, so let's explain this. Actually, let me explain this first. So we have this vector space, and I'm taking inverse limit, where the inverse limit is taken through the partial order coming from C1, C1. Okay, and the maps are, so see what one does. So one map reduces P plus 1 to P, and the other map reduces N plus 1 to N. So you see, so these two maps, so first map reduces the first component, and the second map reduces the second component. So together they, so this is the I take it. So given any R, so given any, let's say Q, V, M, Q star, there is a well-defined map to P, V, M, P star for any R, no, N, P. And I is not there, N, P is less than or equal to. Right. So let's go over this a bit carefully. So I'm saying, now let's take exterior Q and Q star and exterior P and P star, where the only requirement is that NP is smaller than NQ. Now, so just think of this, that so you go horizontally and vertically, or you go vertically, horizontally. You want to make sure that it does not matter what path you choose. Any path, you don't have to go first horizontal, vertical. You just choose any path. So you have to go from this point . Let's say you have to go from this point to this point. So whatever path you choose, it does not matter which path you are going to take. It's a simple linear algebra. I mean, okay, so that's this. And once we understand that this Grassmannian is, again, these maps are exactly like that. So we have a well-defined map for Q, V, M, Q star to P, V, M, star. Again, for M and P, that's equal to that.
Well, Shrawan, where, in what category are you taking your errors? In what category are you taking your inverse?
That's right. Okay. So this is in the category of vector spaces. Okay. So this is just like whatever, undergraduate inverse limit of vector spaces. Nothing funky is going on there.
Yeah.
Scheme wise, also, as I said, this is the honest inverse limit. These are sets, right?
Okay.
These are schemes, but these are sets. These are varieties, but these are sets.
So you can set theoretic inverse limit.
Set theoretic inverse limit. And what happens that, I mean, that's a general fact that when you take schemes of finite type, actually you don't even need schemes of finite type. You take schemes of, let's say schemes of affine schemes, and you take the inverse system of affine schemes. You take the limit as a set as a scheme structure. So this is, and in fact, not only scheme structure, this is an affine scheme. So this fellow, this of course is an affine scheme, it's a vector space. This is an affine scheme.
This forgetful functor creates units.
So
This forgetful functor from affine schemes to sets creates units.
exactly. And so, but the warning is that even though this is an affine scheme, but it's not an affine scheme of finite type. Okay, so you should keep that.
Which maps did you use for those maps?
It's
The C or the K?
yeah, do both. No, you have to do both. Because when you want to go horizontally, you use one. And when you go vertically down, you go
Yes.
the other path. No, you have to do both. But you use whatever you like.
Okay.
You get bored by one path, you take another path. Okay, so now, now the third object is GL infinity. Our good old GL, and this is the direct limit of the GL and this is the direct limit. Now, because B and B is sitting inside the next one, so I can take the direct limit and I get GL infinity. And I will also be interested in its normalizer of the torus, which is nothing but, okay, movement.
So what is GLP?
One minute, let me just write this and then I will be with you. And I can use it. Let me finish this. And B is the normalizer. Okay. Torus. Starting with this. And GL. Yes, what is the question, Mark?
What is GLP?
GLNP is nothing but GLVNP. I want to be, yes, yeah. So VNP is a vector space, and I just take the corresponding GL. Okay, so, and it comes with a basis, so it is actually.
There's a group, it's GLN plus B.
Yes.
Yeah.
Yeah, but I want to keep this.
No, I understand.
And
Because
that's
because
very,
of
very
the map.
important that I keep my N and P separately. I don't want them to collide with each other. So, what was it? Right. And that's why the notation you will see this is half. And similarly, that's half. Okay, very good. Right, and also, let me also, because I need that also, and this is the infinite symmetry group. And this is infinite symmetry. Same. Okay. So this is the symmetry group. So of course, the symmetry group S infinity is sitting inside N infinity, and that's sitting inside G. Right. Okay. How do we reach? Okay, so now, so Right, so this comes, so now comes the main conjecture. So having all this notation, now I can state it. And this is by John Draisma. So let K be any field as ever. Then the infinite Grassmannian. I mean, okay, affine person. So affine Grassmannian. Yeah. Okay. Each topologically H1 topologically S infinity. I will explain all these things. To topologically N infinity Noetherian. And 3 H algebraic. That's it. So these are successively stronger persons. One implies two implies three. No, sorry, other one. No, I said that. So this is the weakest person, more strong than. Okay, so let me explain the things here. So, let me write the. Now again.
Right, Shrawan, can you just say again what the logical dependence is? 1 plus 2 plus 3 or
One, let me,
3 plus 3?
I will first be the children.
Shrawan, you will have to bring the top board down and then raise that one up.
But he has to erase it.
I see.
It becomes
Oh, that's what you said. That's what you said, but let me first erase. Yeah, that's right. That's right.
So while you're erasing, let me just ask, so if the scheme is a.
Just give me 1 minute. Just give me 1 minute. Okay.
Yeah, so if the scheme is a pro option.
Right.
And the group is an in group, as opposed to having a pro group acting on the main scheme.
Any group acts on the probes.
Yeah,
That's correct.
but usually one looks at in schemes and pro groups acting on them. In this case,
Yeah,
the opposite.
Yeah, here it is the end group is acting on probes. That's right. Somebody else had some other question.
No, it was.
No,
Can you say again what the logic of which of these three things is stronger?
Right, okay. So let me write it and then it will be clear exactly. So first of all, what is the meaning? So we have one escape, fine escape. Now topologically S infinity Noetherian means that so oops. Oh, one. So logically, S infinity will fail. What it means is that, so let's call this variety this is Q X. So X, so there is no increasing set of closed subspaces. So since this is a scheme, there is a topology. There is the Jersey topology, right? So in the Jersey topology, you can, so if you had, right, no, let's write that, where each xi is a closed subscheme, and stable S. So as I said, this variety scheme is acted on by G at infinity in the natural way. Maybe I did say that. Yeah, I did not say that. But very naturally, G at infinity acts on this scheme naturally. Okay. So in particular, all these subgroups will act. So now, so this topological S infinity Noetherian means that let's take a ascending sequence of closed subschemes, which are all S infinity stable, then it is stabilized. So then it is stabilized. And the meaning of second is exactly the same. Any ascending sequence of closed subscripts which are n infinity stable will stabilize. Okay, so this is weaker condition because we are looking for less sequencing because this sequencing now should be n infinity stable. So we are so 2 is weaker than 1. Okay, now 3. What is 3? So 3 is similar, except that let's take, oh, maybe I got it wonderful. Let me say this. Maybe I got it wrong. So I think I got it wrong. So yes. So if I take, okay, so minimum. So meaning of 3 is that we cannot, so I and R is stable on that. In this case, in the third case, S infinity. And I will ions. In the affine coordinate ring on K-41. The rotation was Grassmannian. So let's take the affine coordinate ring of that. It's an affine scheme, so I take the affine coordinate ring. Now, if I take any sequence of ideals there, which are all S infinity stable, then this conjecture will say that it stabilizes. So conjecture part 3. It states that star is stabilized. So that is what the third conjecture says. So what I said was wrong. Yeah, sorry. Okay. Now this is okay. So now, sorry, can I just confirm? So saying that S infinity acts, yeah, is saying that N infinity acts and the centralizer acts trivially. No. I'm not saying trivial. These INs are stable under the S infinity action.
Yeah, that's the same as an N infinity action, where the centralizer, the torus itself is acting trivially.
No.
Because the S infinity is N infinity proportional by the first. I mean, at least finite places.
No, I'm not thinking of that. Let's be clear here. No, that's not true. What is he said? Yeah, so let's be clear.
Yeah.
So that will make it not the quotient of n infinity. I don't want to do that. I want to think of S infinity as a sub of n infinity and a sub of Gn.
Oh, you are thinking of it.
I want it in my choice stage.
That's a very GLN phenomenon.
So second,
It's a very GLN.
that's right, exactly. So one is to be very, very careful. So there is, yeah. So Gn infinity is acting naturally on this space. So any subgroup will act. So I am thinking of n infinity, which of course is a subgroup. The torus, of course, is a subgroup. Now the Y group, the S infinity, is not a subgroup, but I'm going to think of this as a subgroup, thought of as permutation subgroup. So it's very important. So we must think on S infinity as a subgroup, because as a quotient group, it's not acting. Okay. So does it clarify?
Is it still true that n infinity is a semi-direct product of S infinity and the torus?
Indeed, definitely, that's correct statement. Okay, so now, so are the statements of the main conjecture clear? Okay, yes,
No, it's fine. Thank you for clarifying.
what about?
Would you fix P and let N only go to infinity?
No. All these limits are to be taken with respect to Z plus cross.
That's right, but if you did that, there'll be a simpler conjecture if you just fix P.
The aim is not to make it a simpler conjecture, right? In fact, I mean, our job in mathematics is to make it. Also, it's interface with combinatorics. I'll come to that, yes, but there is a question. Yes.
And is it correct that one implies two and one implies three?
Yes, one implies, let's see, no, two implies, see, one implies two and three.
No.
That,
Two implies one.
no. See,
Yes, it is. Sorry.
no. One implies two, implies three.
Oh, two implies three.
Also, that's right. Because, yeah, okay. Not exactly. So let's say, no, let's be clear. One implies two, one implies three. And this is a very easy statement to make. It's not a deep statement to make. Right? Okay. So let's see. Okay, I want to move on. And now I come to the main theorem. So, conjecture part 3 is false. And not only it is false, in fact, it is false even if it may require ends to be n infinitely small. Okay, so it's not only false with the S infinity stability, but I'm requiring now all the ideals to be n infinity stable, and this still is false. And in fact, not only it is false, in fact, there is an explicit counterexample.
And that counterexample works for any field.
or anything. Yes, that's right. Yes, completely. This counterexample is independent of it. Okay. Right. Now, it's expressed, I don't know if I will get to the actual construction of this. So this counterexample came about by my numerous tries to try to come up with a counterexample, and everything failed, but finally somehow I got one which worked. Okay.
So again, to clarify, this actually then means the two is also false.
No. So one still might be true.
But if one is true, then one implies three, so how can it be false? I don't.
Oh, sorry.
I'm really confused, Sean.
Okay. No, you have a very good reason to be confused because right. Okay, so the question is, right, see, because I said the positive statement and then I'm deducing the negative statement. That's where the problem is. Sorry about that. Okay, so I don't want to get into these words. One still might be true. Okay, three is false, one still might be true. If one were true, so if three were true, one will be true. Okay, if three were true, one will be true. That's why I said I don't want implies to implies to be under the negative statements, and then I no. So my apology here. So let's be clear here. Three is false. That's definitely correct. One still might be true, and of course, if one is true, then two is true. Okay, very good. So now I want to come to is why it's important. So it goes back to some very important results in combinatorics.
So if two is true, then one is true. Why does one being true like it's true?
No. See, two is a weaker condition because the chain has to be L infinity Noetherian.
But that's stronger than saying that it possesses infinity.
So why don't they let Shravan finish because they're getting.
Oh,
close to the end.
No.
One implies.
Yeah, right. So let's not get into that. I mean, I don't want to get into this English, which I have screwed up. But three is false, one still might be true, two still might be true. Okay.
Three implies one.
Yeah. Let's not get into that. Sorry, I don't want to get into that. So okay. Right. Okay, so it's significance. So so there is this conjecture due to Buddha. And this says that up to isomorphism, they are only finitely many. Excluded. Minus for the class of k-representable matroids. So that was Buddha's conjecture, and now and then there was a theorem. Let me see now. And this theorem is due to Robertson and Summer. 700 pages and spanning 23 journal papers. They proved the following result. Okay, I'm going to write it here now. I'm towards the end. So they proved this theorem, and this is called WQO in the combinatorial literature. And this theorem I will just state, as long as you don't ask me any detail on what they mean. Each minor closed graph has only finitely many. It will be finitely many excluded minors. Right. So that's the theorem, graph property. Each minor closed graph property. Some class of graph closed. Yeah, each minor closed graph families. Okay. Each minor closed class of some, you are right. Yes, as only finitely many excluded minors. And this was the theorem, as I mentioned, 700 pages from 1983 to 2004. And Distel, as some book in graph theory, he said that this theorem dwarfs any other result in graph theory and may doubtless be counted among the deepest theorems that mathematics has to offer, even though I may or may not agree on that statement. But at least that's what he writes. I mean, okay. Now, this is a conference supposed to have at least some quantum, and I am nothing quantum so far. So there is a quantum WQA, which I will not explain for lack of time. And there is a quantum WQA theorem. And I will not explain. It's very similar to here. Now, what is the connection between these two? Oh, my time is up here. So what is the connection between these two? So once one is true, it will basically imply this stronger version, this quantum WQA. And the connection, so let me write, the connection is very simple, but it's very useful connection. Okay, so let me write this.
Does quantum WQO imply WQO? Does the quantum theorem imply the big theorem? Does quantum WQO?
Yes, that's right. Quantum WQA will imply that's right.
WQO.
So you see, okay, so let me just say in few words, the quantum WQA, so this theorem of Robertson and Simmer, it says each minor closed class of graphs, and this says about matroids. So each minor closed class of matroids. So graphs just gets replaced by matroids. That's the difference. So I could have just said here. So if I replace graphs by matroids, then it's the quantum version. Now the quantum version has been claimed, but there is no proof. The proof has not been produced. And in fact, the authors of that paper, so Gillen, Gerards, and Whittle. Okay. So these three people, Gillen, Gerards, and Whittle, they have claimed this quantum version, but they said that the proof is too long, it will take a long time. We are just announcing it. We are just announcing it just for sake of it. 46 or maybe what? Maybe 46 journal articles. Well, who knows? Okay, so let me state a theorem. And actually, I would probably even downgrade it lemma proposition. So let K be any field. Let K be, actually, I want it to be finite field, sorry. Let K be any finite. So far, whatever I've said works for arbitrary field, but this theorem, maybe it works for arbitrary field, but its interface with combinatorics requires it to be a finite field. And assume that the set of K points of is infinite Grassmannian. G, yeah, Grassmannian, infinity by 2, G infinity star. This equipped with the just K topology. Each satisfies one. With the power of the above conjecture. Then matroids representable over K are well ordered by minor. So the order is just minor. So you take a matroid, take its minor, that's the well ordering. So this theorem, as I said, in fact, my time is fast. Well, oh, you are the boss. Yes, yes.
We can go over. No,
No,
We have no. I want to respect that. So, okay, can you give me 2 minutes? So what I want to say that my interest, because I worked in these Grassmannians for too long. So I thought that maybe one can crack on this one and get something very deep in combinatorics and graph theory. But one is open, but this theorem, as I said, this is the limit. And clearly this is the thing. Because we say matroids representable over K are well ordered by the minor order, so there cannot be infinitely many minor orders. Okay, so this theorem is very easy to one page. So that's the connection. So as I said, for 3, I produced a very explicit counterexample. But this counterexample, unfortunately, does not provide a counterexample to 1. I'm still hoping that 1 is true, but I mean, I don't have opinion one way or the other. This is conjecture of Draisma, so I will not be responsible one way or the other. Okay, so I think I will stop here. You have a question, but you can ask me.
Reference.
So maybe we can
Reference
take the speaker first.
Reference for my work is the same title as the title of my talk, and it appeared in IMRN sometime last year, I think. Towards the end of last year.
Okay, so I think you've had lots of questions for Shrawan. We'll postpone the rest to the tea break. And since we're 5 minutes over, and the next talk is maybe 10 minutes, it should be in 5, but we'll start the next talk in 10 minutes. Is that okay? All right. Thank you, Shrawan. 10 5, yeah.